wrote my paper on evolutionary changes of the human body. And my thesis for this paper was that the most apparent evolutionary changes in the human body to arise are the transition from quadrupedalism to bipedalism, which may be due to an evolutionary effort to conserve oxygen, the gracilization of bone structure that can most likely be attributed to the progressively sedentary lifestyle, and a change in the timing of molar emergence, which allows for more adequate life histories to be obtained. So, quadrupeds versus bipeds. That is a shift from walking on all fours to two legs, and it's one of the first major evolutionary changes that's been found, and it may have occurred to encourage oxygen conservation. So how do we know when early humans became bipedal? There are multiple anthropological finds, the finding of Lucy and the Taeyong child. So Lucy presented with an almost complete Australopithecine skeleton. She possessed bipedal anatomy, which included a thicker pelvis and a more acute quadriceps angle. And the quadriceps angle is the angle of your femur to your hips. And the Taeyong child was discovered by Raymond Dart in 1924. This child had a more anterior and inferior foramen magnum, which indicated that it carried its head more erect than its predecessors. Essentially, the Taeyong child was an ape-like hominid that first demonstrated bipedalism. So what changes had to occur for bipedalism to be possible? The foramen magnum became more inferior and anterior. There was an increase in the quadriceps angle. There was a thicker pelvis and a change in the foot shape, a shorter femur, tibia, and fibula, a more anterior ischia, which is a part of your hip bones, and the gluteus medius and minimus became hip adductors rather than hip extensors. So there was a study done to test the efficiency of quadrupedalism versus bipedalism, and Reichland and Michael Sokol at the University of Arizona, and they put 5 chimpanzees on a treadmill to form a quadrupedal gait and a bipedal gait, tested their oxygen output, and then they put 4 humans on a treadmill and measured their oxygen output as well. So the results for the study were that chimpanzees used 75% more oxygen in each trial than humans. And this shows that bipedalism is more efficient, especially in humans, and it's not more efficient in chimpanzees because they don't possess the evolutionary changes that make it more efficient that we just went over, such as a change in the foot shape, change in the quadriceps angle, more anterior and inferior foramen magnum, and those things that we just went over. So another evolutionary change is gracilization, which is a decrease in strength and bone density, which is why this is called a decrease in trabecular bone density, and it can be attributed to an increasingly sedentary lifestyle. So an observational study was conducted to measure this, and human participants were given a CT scan and a microtomography scan to measure bone density along their limb epiphyses. And then fossilized remains of early humans were examined, and their bone density was measured and then compared to the humans. And so the results of the study were that there's a direct relationship between bone density and a sedentary lifestyle, and this was ascertained by looking at the age of the bones for the fossils and then societal norms of the time up to the human participants that they looked at now. And so the change to a more sedentary lifestyle occurred because early humans had to chase their prey down for food, and so they were really active, and as technological advances took place, humans became more sedentary, and some of these advances were modern weapons like the gun and bows and arrows and that kind of thing, and then domesticating animals such as horses because then they didn't have to walk so much. So decreases in trabecular bone density also bring new opportunities for diseases. An example of this is osteoporosis, and when you have osteoporosis, it leads to an either further decline in bone density, so it's kind of a cycle. So the third evolutionary change in humans I want to talk about is molar emergence, and there is a correlation between eruption of the first molars and brain size, and it's been hypothesized that this correlation is due to solid food consumption preceding weaning and molars erupting to provide more efficient mastication. So essentially, the correlation is due to humans consuming food before they leave their parent, or consuming solid food before they leave their parents, and so they need the molars to chew the solid food. So in primates, molar eruption occurs at weaning when about 90 to 95% of brain growth is complete. In humans, weaning, complete brain growth, and molar eruption occur much, much later. And fossil evidence shows that early humans' molars erupted later than non-human primates, but 2 to 3 years earlier than modern humans. So the final thing I want to look at is modern human relatedness. And only a quarter of traits shared by Australopithecines and modern humans can be considered synaptomorphic. Features: post-canine dental reduction and the formation of the pelvis. And this lack of shared traits can be attributed to genetic drift and vicariance. So in conclusion, evolution has allowed for bipedalism, a decrease in trabecular bone density, and a later emergence of molars to occur in modern humans. There are many variable theories for why these evolutionary changes have occurred, but the most relevant maintain that bipedalism to occur in humans to allow for conservation of oxygen and an overall increase in efficiency to allow for survival as Earth evolved, as well as the recent decrease in trabecular bone density occurred due to an increasing immodal society. So that's my presentation. I hope you guys enjoyed it and learned something. Thanks.